All right, let's look at another electrostatics problem. This time, a more involved problem using Gauss's law. We're going to take, to begin, a charged sphere. This is an insulating charged sphere with uniform charge density, and we're going to give it an overall charge of capital Q. Okay, now we're not going to specify at the moment the value that's assigned to that variable Q. We're just going to think about it mostly in general. Okay, so this time though, we're going to take a multi-step process of evaluating the strength of the electric field at different points relative to the center of this charged sphere. Okay, so we want to know what is the electric field here at R1. Next, we want to know what is the electric field here at R2. And we're going to add another piece to this puzzle. What we're going to do is take, now I may go off the edge here of the board, but we're going to draw a spherical shell. So we're going to have a shell, and this is going to be a conducting material. There is no net charge placed on that conducting material before it is brought into the system. So let's see, let's give this a radius A. That's the inside of the hollow sphere. And then we're going to give this a radius capital B. Now that is the outside surface of this conducting hollow sphere. So if you imagine this all together, we have a solid spherical ball right in the middle. It's an insulating sphere. It has a uniform charge density. And then outside of it, is this concentric spherical shell, a hollow shell with internal radius A and external radius B. And so we want to evaluate the fields at R1 inside the the solid sphere, R2 between the solid sphere and the spherical shell. And then we want to also evaluate, I'm going to draw this here, what is the electric field at R3 outside of both spherical, or the solid sphere and the spherical shell. All right, so let's get started. The main tool in our toolbox today is, of course, going to be Gauss's law. The way I always begin with Gauss's law is to draw a surface integral over the electric field dotted with the surface differential, and to equate that to enclosed charge divided by epsilon naught, where epsilon naught is the permittivity of vacuum or permittivity of free space. Okay, so this can simplify fairly quickly. The way that it simplifies is to recognize that in an electrostatic system where you have a spherical symmetry, if your origin is placed at the center of that spherical system, then the vector direction of the electric field created by that spherical amount of charge is in the same direction as your surface normals. So the surface normal in the spherical symmetric picture is going to be exactly the same as the radial vector, the outward radial vector of E. So then this simplifies to still a surface integral, but over E dA, where there are no vector quantities here. So that's very nice. Also E, because we have a uniform charge density, we can bring E outside of the surface integral. Therefore, we simply have a surface integral over this differential area. That, for a sphere, just equals E times the surface area of a sphere. Now, we're going to evaluate at 3 different radii. So I'm going to write this generically as 4 pi r squared. So this is our generic surface area where r can be evaluated at any particular radius that we choose. Okay, good. So we've evaluated then the left-hand side of this equation. What do we do with the right-hand side? All right, the right-hand side is directly proportional to the charge, the total amount of charge enclosed within your theoretical Gaussian surface. Now let's think about that for a minute. At R1, when we want to evaluate the electric field when r, little r, is equal to R1. So this is where our imaginary Gaussian surface, spherical Gaussian surface is at R1. That means that within that imaginary sphere, there will be some total amount of enclosed charge, but it is not equal to Q. Therefore, we need to be able to evaluate, if we drew this imaginary Gaussian surface, how much charge is enclosed within it. So we'll take more steps than is necessary just for the sake of explanation, and we'll be able to see how it simplifies in the end. So we have some total amount of charge Q in the total spherical volume of this inner sphere. Now I haven't given that a radius, so I'm going to label that radius capital R. All right, so if we say that there's a total amount of charge Q in 4/3 pi r cubed volume, then this overall term, this quantity, can be thought of as a charge density. If you multiply a charge density by a volume, then you get a portion of charge. So the volume we're interested in is at R1. So we would multiply this by 4/3 pi R1 cubed. And then a lot of things cancel out. So the 4/3 pi, they go away. And Q enclosed at R1 is simply equal to Q times R1 over R cubed. Now that's got both sides of our original equation somewhat evaluated. All right, so we're going to have then substitute this for the left-hand side, E at 4 pi r squared, but we are evaluating at a radius R1, so we have R1 squared. Now we have our overall charge divided by epsilon naught, so it's Q over epsilon naught times R1 over R cubed. Perfect. Where do we go from here? We want to know what E is at R1, so we simply need to rearrange this equation and simplify as much as possible. No big deal. All right. If we take these quantities over to the right-hand side, we will have that E equals Q over 4 pi epsilon naught. And then we're going to divide both sides by R1 squared. So we get R1 over R cubed. Now that looks good. Okay, and we're done. That would be part A of this hypothetical question that you might see in an electrostatics class of evaluate the field at these different points in this spherically symmetric system. Okay, now we want to hang on to this. I'm going to label this as E1. So I'm going to write that over here. E1 equals Q over 4 pi epsilon naught, and then we have R1 over R cubed. Okay, that's just for safekeeping, so that when we're finished with this problem, we can compare the strengths of these different electric fields. All right, so start again. Part B. We've evaluated the electric field inside the solid sphere. We want to now evaluate the electric field between the surfaces of the inner sphere and the inside surface of this concentric spherical shell. So we're going to evaluate it R2. We're going to draw yet again another imaginary Gaussian surface, so it could be anywhere in between these bounds. Our steps will look very much and mostly identical to our previous analysis. So we can kind of jump a few steps here, and we will write that E times 4 pi R2 squared is equal to, now Q enclosed, for us at this point, what will that be? Well, there is no additional charge in this air gap area right there. That means that all the charge enclosed is just what is contained inside our conducting sphere, and that is Q. So the steps actually simplify here. Rather than need to find a partial amount of this charge, we simply have Q over epsilon naught. And we can rearrange and go right to our solution, that E2 is equal to Q over 4 pi epsilon naught R2 squared. Well, all right, well that was easy, at least simpler than the first part of this problem. So let's put that here. We're going to keep this safe for later. E2 is equal to Q over 4 pi epsilon naught R2 squared. Good. Wow, we're making a lot of progress. Okay, now for part C, or the third part, we want to know, actually, I'm going to throw in something extra here. We will evaluate outside the entire system, but what I want to do at the moment is evaluate right here. Somewhere inside that hollow spherical shell. So R3 is going to be at the hollow spherical shell. I'm going to rewrite this label R1, and then we're actually going to make this a 4-part problem where this is R4. Okay, now it's a complete analysis. Let's see what happens inside of R3. Again, we're going to skip some steps because they're identical to the previous two analyses. And we're going to say, to start, that E3, where this now is our imaginary Gaussian surface, E at R3, 4 pi R3 squared, yep, is equal to Q enclosed. I'm going to write it again, or just as it is here generically, as Q enclosed over epsilon naught. Okay, so we don't have many surprises here, but at least not yet. The further completed analysis of this particular case was a surprise to me when I first saw it. What is Q enclosed? That's the question. Well, because this is our Gaussian surface, we know that we have the entire charge Q inside there. So Q enclosed is going to include Q. It's going to include something else though. One of the keywords, a couple of the keywords used in the description of this problem is that we have a solid sphere, a solid insulating sphere of uniform charge density. That means that static charge can be uniformly distributed throughout the material that makes up this inner sphere. But it's concentrically surrounded by a hollow spherical shell, and that shell is a conducting shell. Its material is different than the insulating material here, and the outcome of that is that a conducting material does not support static charge inside of it. It only supports charges on its surface. Therefore, if you have a positive amount of charge Q in the middle, then that is going to induce a surface charge on this inner surface at A. Since this charge is positive, there's going to be the same amount of negative charge distributed evenly on the inner surface of this conducting spherical shell. Since we're here, we now have Q as part of the charge that it's enclosed, but we also have the same amount of opposite sign charge on that inner shell. So we have plus negative Q. This equals 0. All right. So then the analysis actually can stop now. We have no electric field. There can be no electric field existing within a conducting element or a conducting material. So if we were going to properly finish this part of the problem, we would write that Q enclosed, and thus the right-hand side of the equation is equal to 0. Therefore, E3 equals 0. All right. Great. And that's something very important to remember later, is that anytime you're evaluating an electric field or trying to measure an electric field inside a conducting element, then the charge exists only on the surfaces and the electric field inside is 0. Perfect. All right. Now we are going to R4. Our hypothetical Gaussian surface would be drawn about there. And we want to evaluate what field is set up at the distance R4. We're going to write the left-hand side exactly the same as we did before, but replace R with R4. So we have 4 pi R4 squared. And that equals Q enclosed over epsilon naught. This Gaussian, Gauss's law is a very useful, very powerful tool in electrostatics. Okay, now we have to start counting up charges enclosed. The left-hand side of this doesn't surprise us any longer. Epsilon naught, we know it's just a constant. So we need to evaluate Q enclosed to continue our problem. As in the third part, we have Q. We have this induced negative charge, which is negative Q. But there's going to be something else, another mystery element or mystery charge. Because that this spherical shell contained no independent charge when it was introduced to the system, then its overall net charge must be 0. It must be charge neutral when you look at the entire system. So the presence of Q inside induced a negative surface charge of amount Q on the inside surface. In order to keep this spherical shell at charge neutral, then there will also be the induced countercharge to balance it out. So you will then be able to measure, in this situation, an amount of positive charge that is evenly distributed on the outer surface, and it will have a positive value. So we have positive Q, negative Q, and then positive Q again. So this mystery charge is now positive Q. These two cancel, and Q enclosed actually then is just Q. All right. So we can say that that is just Q. And if we want to solve then for E at radius 4, we would rearrange to discover that E4 is equal to Q over 4 pi epsilon naught R4 squared. Okay, so we've found our fourth electric field. I'm going to list all of these here and save room for us to draw a graph. Our ultimate goal here is to draw a graph of how the electric field changes as a function of distance from the center or the origin. So how it changes as a function of radius. So we have E1 is equal to Q over 4 pi epsilon naught R1 over R cubed. We have E2 is equal to Q over 4 pi epsilon naught R2 squared. E3 equals 0, and E4 equals Q over 4 pi epsilon naught R4 squared. Each of these gives us some indication of what's happening as we increase the radius through these different elements. So we're going to plot a normalized electric field. Normalized meaning I'm just going to divide E in each case by Q over 4 pi epsilon naught. That way we can see directly what's happening as a function of R. Okay, at the very center, it's not hard to evaluate. If you try to draw a Gaussian surface with zero radius, you have zero surface area and you enclose zero charge. Therefore, your E begins at 0 when radius is 0. Okay, if we look at this first equation, as R1 goes from 0 to R, it's increasing. This function increases linearly with R1. So it's simply going to look like this. Some linear function until you get to the value R equals capital R. How about E2? Well, when we ran this analysis inside this air pocket or this free space in between surfaces, we weren't adding any Q. There was no increase in charge. There is, though, an increase in radius. So this equation of electric field is proportional to 1 over R squared. And it's going to look a bit like this. So it decreases on a changing slope as 1 over R squared. Now what about at E3? At E3, once we're just inside this surface, we jump to 0. So there is some discontinuity in the electric field because we go from not, when we step over this boundary of induced charge, we take a step from just Q to stepping over the boundary to 0. All right, so we must then have a discontinuity at R equals A. And then the electric field is 0. It's 0 everywhere inside this conducting spherical shell. So it's 0, 0, 0, 0, 0 until we get to this other boundary of induced positive charge. We take a step over that. So we're 0, 0, 0 until we get to R equals B. And then we jump again. We jump again to this equation. Now, R here has increased, so we are going to jump to some smaller value. And again, E4 is going to decrease as 1 over R squared, and all the way to infinity until the field is actually 0 at infinity. Okay. So hopefully this is a helpful look at how to use Gauss's law and also a helpful look and reminder of how to treat charges when there is a conducting element present in the system. Thanks for watching.